Interoperability is one of the key strengths of FEM-Design. It enables seamless collaboration across workflows and project stakeholders. FEM-Design 25 builds on this foundation with several important improvements. For its users, FEM-Design provides a wide range of integration possibilities, both at local and international level. Alongside direct, purpose-built connections, one of the most widely adopted communication standards in the BIM world is the Open IFC format. IFC enables platform-independent and reliable data exchange between different disciplines and software solutions. Today, nearly 500 registered applications support IFC standard. Of these, around 20% already support the latest schema version, IFC 4.3, now including FEM-Design 25. Beyond being the most advanced Open BIM standard available today, IFC 4.3 introduces a new focus area, linear infrastructure. It addresses the specific requirements of bridges, roads, railways, and waterways. FEM-Design doesn't aim to model full infrastructure routes, but it is fully capable of analyzing and designing the related structures, such as bridges and overpasses. The components of these structures can now be imported either as reference objects for later analytical conversion or load referencing, or, depending on their type, directly as analytical elements. A BIM project typically involves multiple participants who provide essential input for structure analysis and design. This may include data related to different structural element types. As a result, several structural and reference models can arrive via IFC and need to be federated within a single analysis project. This is now supported for IFC files using the existing paste command. After importing an initial model or model part, the process can be repeated for additional IFC files. During each import, the model hierarchy, layer, and object type filters can be configured. Analytical element mappings, as well as material and cross-section assignments, can be defined, or previously created import templates can be applied in a single step. Finally, the inserted content can be positioned precisely within the project. In addition to structural objects, reference data can also be integrated. For example, from architectural IFC models, room layouts, together with their functional classification, such as office spaces, can serve as input for defining imposed loads. From MEP IFC models, the position and extent of heavy equipment can be used to determine static or dynamic loads, structural strengthening, or supports. In everyday practice, not only standard and well-classified model objects are exchanged, but also simpler elements or objects with chained relationships. To avoid data loss, FEM-Design 25 can import these as well, primarily as reference objects, or, depending on their geometry, directly as analytical elements. For complex reference geometries, conversion into drawing solids, combined with solid modeling tools, allows the geometry to be decomposed into appropriate analytical elements, for example, splitting a basin-shaped volume into separate wall and slab elements. As a new feature, pie-type objects can also be imported, either as editable analytical bars, such as columns, or as reference objects. Any imported native or reference object embedded into a soil model element can be converted into a single step into analytical pile elements, including the relevant soil parameters. Since FEM-Design supports combined modeling and analysis of superstructures and soil, it can be more efficient to derive the terrain surface from external discipline models instead of defining it manually. This is now also possible from IFC models based on the solid or surface geometry of IfcSite, or from the IFC 4 element type IfcGeographicElement. These often originate from Revit IFC models as representations of toposolid objects. Terrain surfaces from IFC can now be imported either as reference solids or as continuously connected regions, depending on their geometric representation. A new conversion function then allows the imported terrain model or surface to be transformed into a FEM-Design soil element. Once the appropriate soil layers are defined, this results in a properly structured 3D finite element soil model. The new soil conversion workflow is not limited to IFC objects. It can also be applied to connected regions and solid geometries created directly within FEM-Design. In parallel with these import improvements, FEM-Design 25 also strengthens its IFC export capabilities. The main objective remains the same: to make all relevant design data and details available to the receiving parties. For example, the soil model element used in the analysis can now be exported and shared with other software as the solid geometry representing the analytical model's site. As a final example, in large and complex projects consisting of multiple buildings or structures, it is often necessary to share selected parts of the model with a defined position. FEM-Design now allows selected model elements to be exported to IFC using a user-defined coordinate system. Using the dedicated coordinate-based export option, the receiving software places the exported content into its own global coordinate system based on the specified position. We look forward to seeing these new features applied in your future projects.